Hello and welcome to the problem of the day for July 12th, and it's going to be find eventual safe states. So in this problem, there's a direct graph of n nodes with each node labeled 0 to n minus 1. The graph is represented by a zero-index integer array graph, where graph I is an integer array of nodes adjacent to node I, meaning there's an edge from node I to each node. A node is a terminal node if there are no outgoing edges, and a node is a safe node if every possible starting path from that node, every possible path leads to a terminal node. Return an array containing all the safe nodes of the graph. The answer should be in a sorted ascending order. Okay, so we're actually going to draw this graph, and then we're actually going to draw it like this because this array is pretty much this graph, right? So 0 goes 1 to 2 and so on. So we're actually going to draw this graph right here, and we're going to kind of focus on what are the conditions they're asking for because it's definitely a little bit confusing. So we're going to have a 0, 0, have a 1, 2, 3, 4, 5, and 6. Okay, and now we're going to have edges. So let's make this a little bit smaller. So 0 is going to go to 1. Let's actually draw these in another color, right? So 0 is going to go to 1, and it's going to go to 2. Okay, and now 1 is going to go to 2, and it's going to go to 3. Okay, so far so good. 2 is going to go to 5. So we're going to draw that. And then 3 is going to go to 0. So it's actually going to go all the way around here. And 4 is going to go to 5. And 5 is going to go nowhere. Okay, so right away, let's just figure out like what are our safe nodes. So any terminal node is a safe node, meaning, so what's a terminal node again? A terminal node, there is no outgoing edges. So what's a terminal node? So this node right here is obviously a terminal node. And what else is a terminal node? So this node right here, right? So these two are terminal nodes automatically, and so we know that. Now, every other node is a safe node that every single path from that node has to lead to these. What does that actually mean? Well, so what they actually mean is for every single path coming from that node, there have to be no cycles. And so let's take a look. So 0, are there any cycles? Well, let's figure it out, right? Let's see. So actually this 0 to 1, 1 to 3, and 3 to 0, well, that's a cycle, right? So this path will just infinite loop. And so anytime you have an infinite loop, you're not going to have a safe node. So what about 1? Does 1 have a cycle? Well, let's take a look. So 1 does have a cycle right here. Right? So that's a cycle. Going to infinite loop. Then it's going to come over here. Okay, what about 2? Does 2 have a cycle? No, right? 2 only has one path to 5. So 2 is a safe node. So let's add 2 to our results. And we also have 5 and 6 because they are terminal nodes. What about 3? So 3 goes to 0. And then can that loop again? Yes, it can, right? So 3 can go to 0, go to 1, go to 3. That's a loop. So no good. What about 4? So 4 goes directly to 5. So obviously 4 is another one. But this is kind of tricky. So essentially what you could do is you could do some kind of union find, but then that's going to be not the best complexity. But once you realize that, essentially, let's rephrase the question, right? So for terminal node, every single path that reaches the terminal node, like in order for a node to be a safe node, every single path that goes from that node has to reach a terminal node. So actually, if you think about it, if we actually reverse these paths, then we can go down the paths from the nodes, from the terminal nodes, and then if every single path goes to a node, then those nodes are safe nodes. So we can actually reverse these paths, do the same thing, and then it's kind of like I think it's like a class schedule problem where you have in degrees and you can take everything with no in degrees, and those are going to be safe nodes. And then you're simply going to be removing edges. And then what you're going to be doing is you're going to be removing edges. And then once a node has no in edges, that means every single edge that goes into it is safe. So that node is a safe node. So we can add that node to our safe nodes and we can keep going. So let's actually draw that down here. And I'm going to show you what I mean. So what we're going to actually draw is we're going to draw this one more time. I think I can copy it. Actually, let's just try it again because I need to reverse the edges. Okay, so we're going to have a 0. We're going to have a 1. We're going to have a 2. We're going to have a 3. 4, 5, and a 6. Okay, now we're going to draw the edges, but we're going to draw them in reverse, right? So this 0 to 1 is going to go 1 to 0 and so on. So we're going to use this array. So 0 goes to 1 and 2. So we're actually going to say that means that 1 and 2 go to 0. So let's have those go to 0. Okay. Now 1 goes to 2 and 3. So 2 and 3 are going to go to 1. Let's draw that. Okay, now 2 goes to 5. So 5 will go to 2. Okay, now 3 goes to 0, so 0 will go to 3. So let's do that like this. Okay, and now what are we on? I think we're on 4, so 4 goes to 5, so 5 will go to 4, and 6 will go to nothing. So now you can see in this picture, we still have the same terminal nodes, right? So these two nodes are still terminal. So those are going to be in our result, so 6 and 5 are going to be on our result. But now what we can do is we can just go down every single path from our terminal nodes, and then so basically as soon as a node is terminal, we can actually take every node that it connects to, we can delete that path because that path is going to be a safe path, and then every node with no in degree can just be added into our safe node. So essentially it's going to look like this, right? So there are no paths from 6 but from 5. We're going to take every path, we're going to delete it, and then we're going to take every node that actually connects to, and we're going to see how many paths are there left. So essentially, we're going to delete this path. And now this node 4 has no more incoming edges, right? So because this node 4 has no more incoming edges, now it's a terminal or a safe node. We've checked every single edge that comes into 4. It came from a terminal node, so then the reverse has to go into a terminal node. So now this 4 is a safe node. Now we're also going to delete this path 2. Okay, now we do this again. We say, are there any nodes that we haven't yet put into our result that have no edges? Well, yeah, this 4, right? And so this 4 is safe. So that means we're going to put the 4 in here. And this 2 has no more edges coming into it either. So because it has no more edges coming into it either, it is also a safe node. So now we're going to do the same thing. We're going to put the 2 in here. And then we're actually going to delete all of the edges that come from the 2. So we're going to delete this edge. And we're going to delete this edge here. And so this is like a cons topological sort, essentially, where when the in degree of your node is 0, you're gonna take every node that node connects to and subtract their in degree by 1. And then if those in degrees are 0, you're going to add them into a queue, and you're going to keep doing it. So essentially, now that we took every edge from 2 and we deleted it, now we have to check the nodes again. And we have to see, does any node have an in degree of 0? Well, this 3 still has edges coming into it, this 1 still has edges coming into it, and this 0 has edges coming into it. So these nodes, you can't delete these edges because the only edges we can delete are edges from a safe node. So we're essentially reversing the edges, and then we are deleting edges from the safe nodes. And then if a node has an in degree of 0, then we can make that a safe node and we can delete those edges, right? But as you can see, this 3 does have an edge coming into it. So it's not in degree 0. It has one edge coming into it. So it's in degree 1. This 1 has an edge coming into it in degree 1. And this 2, or the 0, has an edge coming into it in degree 1 as well. So now we are at a point where we still have edges, but then none of them have 0 in degree. And so we are pretty much done with the algorithm, but we're going to return these. But let's say that 3 was a safe node somehow, right? Then we would keep going, right? So we would take every single edge from 3, we would delete it because it's a safe edge, and then we would take all the nodes that we would check the in degrees again. So this in degree would be 0 now, and now this would be a safe node if that was the case, right? So this would be a safe node. Now we would delete all the, so we would put the 1 here. Now we delete all the edges coming from the 1, and we'd make this in degree 0, and so on. And then this would be also a solution, but those are not the case. So that's essentially our algorithm. Once again, to repeat, we know that we know the terminal nodes. We can flip the edges, and we can just take every edge from the terminal nodes and delete them. And then every node that has no more edges now becomes a terminal node or a safe node. And then we can take all those nodes and delete all the edges that are coming from that. And so we're going to keep looping as long as there are nodes with no edges coming into them. And then finally, we're either going to go through every single node, or we're going to have some nodes that still have edges coming into them, but we can't do anything about it, right? We can't get rid of them, like in this case. And so this is essentially if you can think about it, it's the same thing as the taking the classes, right? Like let's say you have a schedule of classes, and some classes depend on each other. Like you have to take some classes to take some other classes, but sometimes you can have a loop, right? Like let's say you need class 2 to take class 3, you need class 3 to take class 4, you need class 4 to take class 2. You're going to have a loop, and so you can't really start any of them because you're never going to be able to finish it. But if you need class 1 to take class 2 to take class 3 to take class 4, and so on, that's going to work. So that's essentially our algorithm, and now we have enough to know what we're going to do, right? We're going to flip. We're going to take every single node within degree 0 because those are terminal nodes. We're going to delete the edges, and then we're going to keep adding on until we still have nodes to add on. So let's take a look at our code here. So this is our code. So we're going to have in degrees for every single node, and in degrees is just the number of edges coming into them. And then we're essentially going to reverse these edges by making a new object with paths. And so we're literally saying, okay, let's just take these arrays, and then for every single edge, let's just reverse that edge, right? So like if 1 goes to 2, then instead, let's make an edge. So paths node, like the key is the node that the edges are coming out of. And so if let's say here, if 0 goes to 2, then we would reverse it and we'd say 2 goes to 0, meaning paths 2 would add 0, essentially. And then for every single node, once you add an edge to it, you're going to increase the in degree, right? And so we actually can get rid of this print paths. Then essentially we are going to have a list of safe nodes, and our safe nodes are going to be, so the way we're going to do it is we're going to have a list of in degrees. And if you think about it, the terminal nodes, if you flip these edges, will have an in degree of 0 because there will be no edges going into them, right? Because a terminal node is an edge that's a node that has no outgoing edges. So if we flip it, it will have no incoming edges. And so for every node that has no incoming edges, let's add those to our safe nodes. Let's also add those to our set. And then what we can do is we can say, while we still do have safe nodes, let's keep popping them. Let's add it to our result set. And then for every node that safe node connects to, let's decrease the in degree of that node by 1 because we're essentially deleting the path from the safe node to the node that it connects to. So the in degrees is going to be 1 less. And then if the in degrees of the path is 0, that means that once we deleted something here, like let's say we deleted this, that means if the in degrees is 0, this new node now has no edges that come into it. So now that is a new safe node. And so if it's a new safe node, we can add it to our safe nodes, and we keep doing this until our safe node is either empty, where we have no more nodes we can add. Essentially, we just keep doing it until safe node is empty, and there's going to be 2 cases. We're either going to go through every single possible node, or there are some nodes that we could just never add because they're circular, right? Like this 0, 1, 3. And so then we have a set of all of our safe nodes, and they ask us to return the answer in ascending order. So it's pretty straightforward. We have a set of our safe nodes, then we just make a result, and we just say, let's just loop through all the numbers in the graph and check if it's in the safe nodes, if it is append. So essentially, you're basically sorting your set in linear time. And then so you append it to the result, then you return the result. And that's pretty much going to be it there. So it's called Kahn's topological sort if you want to check out the algorithm, but that's essentially what it boils down to. And yeah, a similar problem would be something like course schedule. It is a little bit tricky. I do think this problem is maybe a little tougher than a medium because it's a little bit tricky to find out that you need to reverse. And then once you reverse, you can use these in degrees to find the edges that are safe. Okay, so let's actually run this to make sure that it works. Okay, and it does work. And let's think of the space and time complexity here. So for the time, what are we actually doing, right? We're making this in degrees array. That's going to be nothing. Then we are looping through every single node in the graph, and then we're also checking every single value in there. So let's see what they used there for this. So n is graph's length. Yeah, essentially, if n is the graph length, let's just say we can make some variable for how many total numbers there are total, right? So we'll just call that m, maybe. So m is the total number of numbers in all of these arrays. Like if you were to flatten this whole array into one array, that's the total number of numbers that you have. So it's time m. And now let's think of some other stuff here. So what else are we doing? So we're going through the indegrees, which is just n. So yeah, let's just write this down. If n is length of graph and m is length of flattened graph, if we were to just concatenate every single array, right? So if we were to just take every single subarray and make them all into one array, so it would look like something like this, right? 1, 2, 2, 3, 5, 0, 5, and so on. That would be, let's just call that length m. Okay, so m is the length of the flattened graph. Time would be O of m. Now, let's check just to make sure that time is O of m. So this is going to be O of n. Now, here we are going through every single safe node. So, and we're going through every single path. And so there are m paths max, right? Like the most paths you can have. Every path is just a value in here. And so this is going to be O of m. And then what are we doing here? This is O of n because we're just going through the length of the graph. So the total thing is O of m, where m is the total number of actual like edges, let's call it, in this graph. Okay, so maybe we can call like O of e or something, right? So we can just say like e is total number of edges. Okay, now what about the space? So for the space, we are making a dictionary of all the edges. So that's going to be O of e, right? It's actually going to be, I think it's going to be e plus v, because we do have vertices as well. So it's going to be the number of vertices plus the number of edges. And by vertices, I mean these things, which would really be n, right? So the number of vertices is just the length of n. So I think it's e plus v, essentially, or e plus n, whatever you want to call that. And let's take a look at some more. So we go through these indegrees, which is O of n. And also these indegrees are also, yeah, constructing these indegrees is only O of n. So this is bigger, so that takes precedence over that. And in this safe nodes thing, so the safe nodes can hold a maximum of every single node. So that's also O of n. So this is O of n. Yeah, so this safe node is O of n. This indegrees is O of n. And then this paths is O of e plus n. And yeah, and then we have our result, which is also O of n. So essentially, yeah, this is our total time and space, where e is the total number of edges, and space is the total number of edges plus the total number of nodes. And that's going to be it for this problem. So hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I will see you in the next one. Thanks for watching.